so please don't get me arrested and told. All right. Off to the side, on this part of the board, I'm going to remind us what we learned last class about calculus. We learned that since a derivative is the slope of a line tangent to the curve, and the slope of a position graph is velocity, the derivative of position is velocity. We also learned that for the same reason, the derivative of velocity is acceleration. Right? How do you feel about those two statements? We understand that. Cool. Last up, because the integral is a sum of a bunch of small geometric sets, could be lengths, areas, volumes. Since the sum of areas, the integral, under the curve of a velocity time graph is displacement, the integral of velocity is displacement. There we go. And the integral of acceleration is acceleration. I'm sorry. No, I'm so sorry. Is change in velocity. Whoops. And I will prove that later. I'm going to try. My cousin is a nurse and walked up to me yesterday and she was like, I've stolen all of these from my job. All of these. Do you want them? And I said, yes, I do. They're expo markers. They just keep ending up in her pockets. It's like, yes, absolutely. Expo markers. Let's go. So this will be an important thing that you'll want to, ooh, look at that. That's crisp. That's beautiful. It's the little things in life. Apparently the hospitals get better stuff than the high schools. Who knew? I will have to raid that more often. There you go. This is going to be really helpful even if I've already taken calculus as a reminder. That means if I need to go from position to velocity or acceleration, I'm going to end up taking a derivative. I'll show you how to do that in just a second. And if I need to go from acceleration to velocity or position, I'm going to take an integral. That's a good cheat sheet as a reminder of what I'm supposed to do. If you have a velocity equation, and you're like, okay, I need an acceleration equation, which one do I do? That's where this comes in. Another way to think about this is that accelerations graphs are always going to be lower powers. So like, if the position is x squared, the acceleration is just going to be a constant. If the position is x cubed, it's going to be the higher power. And then acceleration is the lower power, so it goes that way. So if you know a lot about derivatives and integrals, you know that you get higher power when you take a derivative, or sorry, you get higher power when you take an integral, and you get lower power when you take a derivative. So that's also a great way to check yourself. Oh, I have a velocity equation, it's a quadratic, and I found the acceleration equation. Well, if my velocity equation is power of 2, I should expect my acceleration equation to be a power of 1. Or if I go to position, it should be a higher power, power of 3. So that's just a good way to check yourself. So I put that over there too. All right, it's time for the derivative. Yay. Again, it's the slope of a line tangent to the curve. That's all it is. That's why it represents velocity and acceleration, because it's just the slope of the curve. Cool. First things first, you will most likely not see me do this on the board very often, but it is the way we write a derivative, so let me show it to you, because you might see it on an FRQ. When I write a derivative, I write it like this. This is saying the change in something with respect to the change, in this case, in x. So you would see this if I'm just hanging out in calculus class and they gave me an equation, not even a full equation, they just said, take the derivative of cosine x. A lot of times you see it as dy dx in calculus class. That's saying the change in y with respect to a change in x, which makes sense if this equation is y equals cosine x, then I'm saying the change in y based on the change in x. That's where that comes from. So this is how we actually write a derivative. The most important part about it is the bottom. The bottom tells me what the actual variable is. This tells me what variable is the variable. The variable. What I mean by this is that I can write an equation a x squared plus b x plus c. And you can make the assumption that x is the variable, but what if it wasn't? What if I said take the derivative of x with respect to a? That tells me a is my variable. Everything else then is a constant. Everything else then is just a number. Even if it's a letter, even if it's a variable, it's not the variable. It's not the one that's allowed to change. I might not know what the value of x is, or the value of b is, or the value of c is, but it's now a constant. So when I say the bottom is all that matters, it's telling me what part of that equation is the variable I'm paying attention to. Everything else is a constant. Okay? In calculus, it's always going to be x, so like we don't have to deal with that. But in our class, it's really never going to be x. Instead, here's the ones we're going to have. Here are the two that we're going to have. That would be really weird if your calculus teacher did that. We're going to have these two, dx, dt. That is a change in position with respect to a change in time. So if I think back to what I know about physics, change in position over change in time is equal to what? Velocity, right? Change in position over change in time. This is my velocity derivative. So, most importantly, if I'm asked on an FRQ to find dx dt, they're saying, please find the velocity. I'm probably not going to write this out when I just do practice problems very often, but this is a way they could say velocity. This is another term they could use to say the word velocity. For acceleration, it'd be dv dt, right? Change in velocity over change in time. I'm going to show you how to do a derivative, and I'll write the full definition on the board. And when I write the full definition on the board, I'll include this. But like, when you just go and take a derivative, you don't really write that down. I don't write it down. You can, but like, it's not that serious. All right. Here's how derivatives work. When you go to take a derivative, what you're going to spend the first half of Calculus BC doing is learning, it's just rules. You just follow a set of rules. That's all a derivative is. You don't actually like learn some magic. You just learn, okay, when I take the derivative of this type of function, it looks like this. When I take the derivative of that type of function, it looks like this. When they start to combine functions, it can get ugly. But until they do that, if it's just one type of function, then they're just going to tell you the rule, okay? And that's what I'm going to do today. So for example, two rules that we will not have to use very often, but maybe one day you might use in my class. The derivative of sine of x is just cosine. That's the rule. If you ever need to take the derivative of the sine function, it's just cosine. Like that would be the rule. The question question in calculus class would be, hey, will you find the derivative of a sine? And you'll be like, yeah, it's cosine, thanks. That's the rule. And you just follow it and then you're done. That's a derivative, they're so nice. The rule we're actually going to use today, and the only one we need for this unit, is the power rule. Power rule works on a power function that looks like this, x to the n power. So for example, that could be x squared, 3x to the 6th, just x, just a number. That's a constant, it's a power function. What power does it have? 0. Its power is 0, right? All of these are power functions, all of them. And here's the derivative of one. The derivative of a power function, x to the n, is, anybody want to help me out? Just taking calculus? Yeah?
Nx to the n minus 1.
Nx to the n minus 1. That's it. That's the rule. That's all you have to do. Okay, we're going to do a couple examples, see how easy it can be. So for example, if I say, take the derivative of x squared. So in this case, n is 2. So I multiply 2 out front, and then it's x. Because my power should now be n minus 1. 2 was the original, 2 minus 1 is 1. Okay, let's do another one. D over dx of 3x to the 6th. Okay, I'll just do what I have up there. That number out in front is not what I'm taking the derivative of. I'm taking the derivative of x, so I don't care that it's there. It's just going to stay there. I can rewrite it as 3 times the derivative of x to the 6th if you feel the need, but mostly I just don't care. Like, it's just a 3, it's still going to stay there. Yay, 3 times, what's n in this case? 6. 3 times 6, and then x to the now what? 5. So this is n. So I have n multiplied out front, raised to the n minus 1. So I get 18x to the n. Power rule is additive. So if I have something longer written out, like x squared plus 3x plus 8x cubed, I just do each individual piece. Doesn't get hard, just do each individual piece. It's additive, so I'm just taking the derivative technically of x squared plus the derivative of 3x plus the derivative. Your calculus teacher can show you the details. But what would this be? Let's see, somebody, the first term, that's not the correct list at all. Annika, what about the first term there? That's going to turn into 2 to the x, right? Sai, what about the second term, 3x?
1.
3. Just 3.
Just 3?
Just 3.
1 times.
Yeah, 1 times 3, right? So the x just becomes 1. So it's 1 times 3. Yep. And then 8x cubed, that term, Krish, what does it turn into?
Which one?
8x cubed.
Just turns into x cubed.
No. So I'm going to multiply 3 times 8. Yep. And then I reduce this by a power of 1. Yeah, x squared. That would be it. So that would be the derivative of that guy. One thing to note, the only other thing you need, and I'm going to give us a couple to practice. If I take the derivative of just a number, well, it becomes 0. So just a number, that's just a constant. There's no x at all, so it just becomes 0. Okay, so let's practice a couple. I want you to take the derivative of these 4 equations and see if you can do it. especially if this is new to you, see if you can get these. What are the derivatives of these questions? If you need additional help, have a question, now break down now.
I have a question. For 4, what are we in respect of T or F?
Shoot, I wrote a T. I'm not supposed to do that. That's a good question. Hold on. It's physics, so I always write T's. This is an X. It's an X. Good check, good check. I'll do that sometimes. The hospital markers have a different smell than the Expos, I believe. Yes.
You know what you're talking about? I forgot that.
Yes.
He asked, but what if he just came flat?
These are the last two that I have. Or my last one.
I love it. Wait, do you have noticed in the last
Any questions? Those look good. You're good. You're good. How's it going back here? Do you have a question? No. That's okay. Those look good. I'm gonna put the answers in Z.
Dude, I'm so done. Because the times
Alright. Check your answers. Anybody have any questions based on those being the answers? Alright, that's the actual calculus of it all, but let's apply it to physics because that's why we're all here. We've now learned how to do the power rule, take a derivative. Let's apply it to kinematics. Okay, so when you got the kinematic equations last year, they were given to you under the assumption that acceleration was constant, right? That's what we said. These equations work if acceleration is constant. I'm going to prove that to you right now using calculus. If I start with the equation on our equation sheet for position, looks like this, plus 1/2 a t squared. That's the equation for position that we see right there smack dab front row on the equation sheet. I'm going to find the acceleration based on this equation. So if this is my equation, and I take the derivative of x with respect to t of all that, I would get a velocity. That's not my variable. My variable that I'm deriving based on is t. So that just makes xo a constant. Constants go to 0 when we take a derivative, so that goes away. This is a number times t. The initial velocity times t. So if I take the derivative of that, it just becomes vx naught. This one is 1/2 a times t squared. So if I take the derivative of that, I'm going to multiply 2 out front, which cancels, and leaves me with at. And that is the velocity equation. That's number 2 on the list. Yes, question?
Why would you leave the A?
Because the a is still a constant, and it's since this term isn't going away, it's still multiplied by a. So all I do to change this term is multiply 2 to the front of it as well, and so the a didn't go anywhere.
Okay.
Good question. If I take one more derivative, do that for this equation, I get that acceleration. Vxo no longer has a t next to it, so it makes it a constant. It's going to go away. 0 now. Plus a times t. The t goes away, and I'm left with, yep, constant acceleration. So the kinematic equations are based on constant acceleration. And I can take the derivative of the position function, then of the velocity function, and get to that right there. Right? Now, what's going to happen right now on an example is that I don't have to, now that I've taught you that this is how we got those equations, you now have the tools to get equations even if acceleration isn't constant. So these were the equations, we gave them to you, we said, here you go, we're only going to use constant acceleration. But now, the world is our oyster, because you can find your own equations even if that's not true. So that's our first example using calculus and kinematics. If the position of an object is given by, let's say, x is equal to negative 3t cubed plus 6t squared. When, aside from t equals 0, is velocity 0?
Is that cubed?
This is cubed, and that's squared. So, basically what I've done here is instead of starting with the position function we have on the equation sheet, we're given a new position of equation. In this case, negative 3t cubed plus 6t squared. And this is asking when, aside from t equals 0, is velocity 0? Well, to answer that question, I need a velocity equation. I don't have one, so let's go get one. This shows me that if I want to go from position to velocity, I take a derivative. We learned how to do that, so let's try it out. I've got position is negative 3t cubed plus 6t squared. What would be my velocity equation? Try and do it yourself real quick, then I'll ask somebody. So you're trying to take this derivative and find the velocity equation. Anybody feel confident and want to share? Yes,
With the answer, or like
just the velocity equation.
negative 9t squared plus 12t.
Yes, negative 9t squared plus 12. That's my velocity equation. I took the derivative, and that's my velocity equation right there. Questions about how I got that? All right, now this is just a algebra question. I've done the calculus, that's it. Now it's an algebra question. When, aside from t equals 0, is velocity 0? So what should I do to this velocity equation to solve this? Set it equal to 0. This is a plug. If you were a person who immediately at this moment would stick this into the problem solver on your calculator, stop doing that. You're an advanced student who is going to eventually take probably some level of advanced math classes that might not have calculators in them. And if you are unable by that point to do this simple factoring, because you haven't done it in 4 years because you've used the problem solver because sophomore year somebody showed you how to do it, and you're like, oh wow, cool, awesome. Okay, and you don't know how to factor this, your life's going to be pretty bad. So, don't do that. I simply factor off a t, and I get negative 9t plus 12. So that would get me 9t is equal to 12. So it would be 0.75. Oh no, 1.33. Sorry. 1.33 applied. 1.33. So that's the time I got my final answer, yay. Calculus was just a step. This is what's new, okay? Everything else, when we go to projectile motion next class, it's gonna be the exact same stuff. We don't even do this calculus with two-dimensional motion. We only do it with one dimension at a time, either horizontal or vertical, okay? And we really don't even do it with vertical because this is the world of actual physics. We're on actual planet Earth. So what is the acceleration in the vertical direction? Negative 9.8. Unless you're on a rocket ship with a delayed release and you could write some fancy equation for your acceleration. Otherwise, it's just negative 9.8. So most of the time, you'll only see this in a horizontal question. Okay? But this is a new thing. Used to, you had those three kinematic equations, you just use those to solve. Now the new thing is, you have to find, using calculus, the equation, and then solve it. So that's what we're doing here. Okay? Questions about this? You'll see more examples in the future. All right, integrals. Yay, integrals. The bad part about integrals is they are worse than derivatives. I don't think there's a single person who's taken calculus DC who won't agree with me. Integrals are worse than derivatives because there aren't a lot of rules. Like derivatives, they're just going to tell you here's the rule. And when things get tricky, there's a way to solve it. Integrals are harder because integrals are just the opposite of a derivative. That's all they are. They're just the opposite. If you take the integral of something and then take the derivative of it, you get back to where we started. Let me show you. If I take the derivative, the integral of a velocity equation, I'm going to get a position equation. If I then go take the derivative of that position equation, I go back to velocity. They're just the exact opposite of each other, which makes doing difficult integrals harder because you don't just have a rule that you have to follow. You have to basically undo the derivative, which is much harder. Luckily, power rule, pretty simple. So, for an integral, it is, at the end of the day, a sum. That's what it is. It's a sum. Maybe at some point in your math career, you've seen this symbol for a sum. That's a sum, right? That's a sum if I can take a sum of like a specific number of things. There are 27 of you. If I added all your birthdays up, that's a sum. I could write it out using this epsilon, and I could say that's a sum. I could even do it if I asked for all the birthdays of everybody in the whole school, because that's like 3,600 people. I can still do a sum. But an integral, we talked about last class, is an infinite sum. I take the sum of an infinite number of things, not just the number of people in this room, this building, this state, this world, an infinite amount. And when I do that, instead of this very clunky s, I get a new s. That is an integral sign. That's all it came from. Yes, it looks fancy and it's cool, but it's just a fancier s. This is a s for sum. This is a fancier s for an infinite sum. Okay? So, an integral looks like this. The integral of a function with respect, in this case, to x. So that's what an integral looks like all written out. You will write this way more than you write the derivative thingy. You'll barely ever write that. You'll set up an integral with the integral symbol pretty regularly outside of this unit. So this is what an integral looks like. And for the power function, the integral of it is actually easy to write as a rule. It looks like this. So we only have to do the integral of the power function right now. And it's pretty simple. It is a rule. A lot of integrals aren't. It's just the opposite. But this one's pretty simple. So what this says is that I take whatever n is, and I add 1. And that's the new exponent. And then I have to divide by n plus 1. So let's see an example. I'll put it right here. Starting with x squared. N is 2 plus power, and then whatever the new power is, I divide by it. Right? Kind of the opposite of multiplying it out in front. Yes?
Are you just gonna ignore like plus C?
I'm getting there. I'm not going to ignore it. I'm getting there. Don't you worry. Don't worry. So, as I said, integrals are the exact opposite of derivative. They're oftentimes called the anti-derivative. And here's how I know I've done an integral correctly. When I get this, if I go and take the derivative of it, try that. dx of x cubed over 3. You learned how to do a derivative. Take the derivative of that. I would multiply 3 out front, which would cancel. And then I subtract 1 from the exponent. What do I get? X squared. Very nice, very nice, very nice. I get x squared. Let's try this one more time. What if I took this integral and it actually was that plus 100? If I take the derivative of x cubed over 3 plus 100, what is it? What happens to the 100? It becomes 0, right? So I still get x squared. I can make this number anything, absolutely anything. Any number I could come up with could actually be hiding right here. And it would still be the antiderivative of it because if I take the derivative, I still get x squared. That's a problem. And the way we solve that problem in calculus classes, we say, okay, any integral we take, we have to add c next to it. C represents any constant, some number, any number. I don't know what number, they don't know what number, some number. But the integral of x squared is x cubed over 3 plus any constant. Because if I take the derivative of this statement, I get back to x squared. Now, this is an indefinite integral. We're going to do definite integrals later. Indefinite integrals need this c. They're less defined and they need this c. Because they could be anything, right? Because all I have to do is take the derivative and I would get back to where I started. Is that for me?
This one is for you.
Wow, thank you so much. I'm so excited. Look at my recycling bin, guys.
Bye, Miss Limer.
Bye. Now in physics class, it's very rarely going to be C. Because as I show you in just a second, that C is probably defined by something physical. In math class, it could be anything because, hey, I don't know what this function represents. It's just x squared. I don't know what that is. It's just a function. So C could be anything I want. If I'm taking the integral of an acceleration function to get velocity, I'm going to pretty easily figure out what C should actually be. Okay? We'll talk about that in a second. Let's practice a couple of integrals to make sure we're good on that, and then we'll do the physics of it all, and then we'll be done for the day. Whew. Trust me. It's a lot for me too. Alright, so just a couple of integrals, because I do think they are the trickier of the two. Say x cubed x to the 6th try those three. Try taking those integrals. If you're new to them, try them. If you're not new to them and somebody at your table is, help them. You want parentheses here? Sure. That will make you happy. I'm not a calculus teacher, so I don't have to do that kind of stuff. That's my actual answer to the question.
Oh, yeah.
Oh, no, you're fine.
So it's a little bit trickier. We're doing division now. That's mainly the trickier part. Division. Yes, the first one's right, Abraham. Yes. It is a constant. When I take the derivative of a constant, it goes away, right? But when I take the integral of a constant, this now you can think of it as having the power of x to the 0 next to it. And so then I would add 0 plus 1, so now I'm going to have an x next to it. Does that make sense? Yes, first one's right. Fractions stink. I mean, that's okay, so don't forget to put plus C next to it. Yeah.
Even when it's like this.
Yeah, you're right. Plus C's gotta go next to it. It's a very pretty note.
We just spawned it at the X.
The answers are on the board. If you have a question, raise your hand. So you'll notice when I integrate, constants don't go away, they magically get an x best friend. That's because technically I can write this as 8 times x to the 0 power, right? That's the same thing as 8. And so I do have an x that has an n. I add 1, and technically I divided by 1. This is still 8. Questions about these? This is as hard as it gets. I just want you to know for at least this unit through Friday of next week, right? And honestly, in forces it can get a little bit trickier, but not by that much. Okay, it's still the power rule for a long time. Anybody have a guess the first time it's probably going to turn into like a sine or cosine function? Simple harmonic motion? Ah, darn. That simple harmonic motion of it all. Alright, I want you to try this. We'll go over it, but try it out. Work backwards. If acceleration is constant, find me the velocity and position equations. So if I want to take the integral of acceleration, in terms of t, right? T is what we integrate and derive based on. That would be, this is just a constant for now. So this would be my velocity, and it would be a times t. Now I would have to put a c there, right? But this is an actual physical relationship. That c would be my y-intercept. It would be my velocity at time 0, which we have a name for. Hey, cool, we have a name for that. What is it, the name for that? Initial velocity. There you go. And now we've got back to those darn kinematic equations. If I take the integral of the velocity equation, I'll write it correctly this time. That's going to be my position function. So I would get, this is a constant, so it's going to add a t next to it, v naught t, plus, okay, this is t, it's now going to be t squared, and I have to divide by 2. Hey, that looks an awful lot like 1/2 a t squared. Plus c, there's the c of it all. I will tell you this about the c. Their favorite thing to do, if they ask you an question that's not overly complicated. Like, on E&M, you won't see this on E&M, but on the mechanics test, their favorite thing when you do an integral and get something like this is to ask you, one of the questions on the FRQ will be, and what does the C represent? And in this case, what would this C represent? If I set time to be 0, it would equal C, so what would C represent? Initial position. That's a question they will love to ask you on the test. They'll make you do a very simple integral, not the hard ones. They'll make you do a simple integral, and then they'll ask you, what does that C represent? I will tell you a lot of times, and we'll go over this when we get there, it's that simple harmonic motion one, and the C will represent maybe the extended position or the middle position or something like that. That's where they came from. If you take constant acceleration and take the integral of it, you get to our kinematic equations. Questions about this? All right. Last example, and then you can do whiteboard problems and ask me loads of questions, and then you can go let your brain rot about this for a couple of days and come back and be like, okay, calculus isn't that scary, I'm okay. I'm gonna make it. All right, my last example. If the acceleration of an object is A is equal to negative 6t plus 8, and the initial position is 3 meters, the initial velocity is 12 meters per second. What is the position at 10 seconds? So I've been given the acceleration equation, and I'm asked to find positions. So that means I'm going to integrate from acceleration to velocity, and I'm going to integrate from velocity to position, and I'm going to get this full equation. So, A is equal to negative 6t plus 8. My velocity would be the integral of that.
Is that a negative?
It is a negative. It is a negative. So, the integral of that, this is just t, so it would go up to being t squared, and I would have to divide by 2. So I get negative 6t squared divided by 2. What does that simplify to? 3, right? Negative 3. So everybody see where I'm going to get that negative 3? I raised it to the power of 2, and I divided by 2, and that leaves me with 3. So I'm going to write that. Negative 3t squared plus 8t plus my initial velocity. What was my initial velocity? 12. In this case, it was given in the question. They can do that. They might not give it in the question, and you might just have to put V naught. Or, something I've seen in the FRQ to be aware of, they'll just like sneakily somewhere in the FRQ give you this. So they won't tell you what the initial velocity is, but they'll give you a velocity time graph, and you'll have to find the initial velocity from that. I've definitely seen them do this. So they'll like show you the graph and then tell you this is the acceleration, and then a lot of students will miss that point because they don't go back and they're like, oh yeah, the initial velocity was 8. Right? They're just like, oh, they didn't give it to me, must be 0. No. My position is the integral of velocity it. So, x equals, this would be t cubed now, divided by 3. So negative t cubed plus, this is now going to be t squared, so I divide by 2, plus 4t squared. This is now going to get a new t best friend, ball of t. What was my initial position? 3. That's my position equation. So then I find, using my calculator, the position at 10 seconds. So negative 1,000 plus 400 plus 120, yes, plus 3. Negative 477 meters. Questions about this? If you have issues with the integrals or derivatives, ask me. You haven't been through calculus yet, that's perfectly fine. I'm here to help you. I'm not here to make this hard. Second, I want you to look at these equations, and before you start the whiteboard problems, which is what we'll spend the rest of class working on, I want you to look at these equations and see if you can tell me a couple of things. Obviously, we know what the initial velocity was. It was 12 meters per second. Can you figure out what the initial acceleration was?
6.
Almost.
Negative 6.
No. T would be 0.
8.
8. Yeah, acceleration at t is equal to 0. Right? T would be equal to 0, that would go away as your statement. Yeah?
Oh.
Yeah. You got it. So, it was accelerating as a positive 8, and it had a positive initial velocity. So, that means it was increasing its positive speed up until some time. Then the acceleration turns negative before 1 second. And it starts to negatively accelerate, slow down, and then it's going to go down forever. Right? So how many times does this cross, velocity time graph for this cross the x-axis?
One, two squared.
Once. It only crosses the x-axis once. If I sketch this velocity time graph, it had a positive acceleration that's changing, and then it would have looked like this. Getting steeper and steeper and steeper. That little hump isn't really there. I just wasn't drawing it correctly. But that's what the velocity time graph. So something, it's not asked very often, but just something to keep in mind to practice and sharpen your skills, is as you make these new kinematic equations, that's what they are, right? They're just the ones that don't involve constant velocity, or constant acceleration. As you make them, try and think about what that motion it's saying actually is, right? Try and think about, okay, what would those graphs look like? How would I describe this motion? It's not constant acceleration, it's something else. This is linear acceleration. Woo. Okay. Alright, whiteboard problems, ask me for help. I will post the answers on. If you're done with the whiteboard problems, then the practice. If you're done with the practice, then I've got nothing for you.
A little bit of distance.